Hello students, this is Vijay Janardan. In the last lecture, we have studied about the friendly adsorption isotherm of our second chapter, that is a surface chemistry. So in this lecture, we will study the second type of adsorption isotherm, that is a Langmuir adsorption isotherm. The basic theory of adsorption of gases on the liquids is due to the Irving Langmuir in 1916. Means in the 1916, Irving Langmuir gave the basic theory of the adsorption of gases on the liquids, and he derived the adsorption isotherm, which is called as a Langmuir adsorption isotherm, and it is based on the following assumption. And the assumptions of Langmuir adsorption isotherm theory are: the first assumption is the surface of solid is made up of elementary spaces. Means the surface of solid is made up of some small spaces which are called as elementary spaces, and each space could absorb one gas molecules. Means the capacity of each elementary space is the absorbing one gas molecules. Thus, the adsorbed layers are no more than the single molecules in the thickness, and intramolecular forces fall off rapidly with increase in the thickness of adsorbed layer. Means the capacity of each elementary space is adsorbing the one gas molecule. Due to this, the adsorbed layer is no single molecule thick, because many more gas molecules get adsorbed on a elementary spaces. Therefore, the formation of thick layer, and therefore the intramolecular forces fall off, means break down rapidly, and with increase in the thickness of adsorbed layer. Means as the thickness of adsorbed layer, that is gas adsorbs on the liquids, so the thickness increases. As the thickness increases, the intramolecular forces decreases, and all the elementary spaces are identical. Means all the elementary spaces of the solid are identical in their affinity for the gas molecules. Means all the elementary spaces have same environment in the gas molecule. Thus, the solid surface has a uniform adsorption properties due to same environment, and the presence of gas molecules on a given space does not affect the properties of neighboring spaces. Means the presence of gas molecules doesn't affect the properties of neighboring gas spaces. And due to the thermal energy possessed by the molecules, means any molecule may possess the thermal energy. The few molecules are detached and pass back into gas phase. Means the few molecules are detached from the gas phase, and they passed into few molecules are detached from the solid phase and pass back into their gas phase, and this process is called as a desorption. Means reverse of adsorption. Firstly, the gas molecules are adsorbed on the solid surface, but some gas molecules, due to possessing some thermal energy, pass back into their gas phase, and this process is called as a desorption. And thus the adsorption process is assumed to be composing of two opposing actions. Means the adsorption process consists of two opposing actions. First is the condensation of molecules from the gas phase onto the surface of adsorbent, and second is the evaporation or desorption, that is the breakdown, evaporation or desorption of molecules from the surface back into gas phase. Means at one time adsorption and desorption are in equilibrium with each other. So at equilibrium, rate of condensation of molecule is equal to rate of evaporation, and due to this the adsorbed molecules get dissociated, and on the basis of postulates the Langmuir derived a adsorption isotherm, and he considered that suppose at any instant a fraction theta of the adsorbent surface is occupied by molecules. Means if the theta fraction of adsorbent surface is occupied by adsorbed molecules, then 1 minus theta will be, the surface will be free. Means theta is the surface which is adsorbed, and 1 minus theta is the surface which is free. And this is illustrated by diagram. This is a diagram. This is the fraction, that is occupied fraction, that is theta, and this is the unoccupied fraction, that is 1 minus theta, and this is a adsorbent. Means this is the surface of adsorbent, and the fraction theta is adsorbed, that is called as occupied fraction, that is theta, and 1 minus theta is the unoccupied fraction, or also called as a free fraction. Means here no adsorption takes place, but in the fraction theta there is somewhat adsorption is taking place. So the adsorbed layer is a unimolecular thick, and that only those molecules striking the surface can be adsorbed. And according to kinetic theory of gases, at a constant temperature, the gas molecules strike the surface at a rate that is directly proportional to the pressure of the gas. Means according to kinetic theory of gases, at constant temperature, the gas molecules strike or collide the surface which is directly proportional to the pressure. Means as the pressure of the gas increases, the capacity of colliding the gas molecules on the surface of solid increases. And we can write in the form of equation, that is rate of condensation is proportional to P into 1 minus theta, and rate of condensation can be also be written as K1 into P into 1 minus theta. This is called as equation 1. Here K1 is called as a proportionality constant, and the rate at which the gas molecules evaporate from the surface will be directly proportional to the fraction theta of the surface that is covered by the adsorbed gas molecules. Means the rate at which gas molecules evaporate, that is the desorption process, is directly proportional to the fraction theta, and it is written in the form rate of evaporation. Here rate of condensation means rate of adsorption. Here rate of evaporation means rate of desorption. So rate of evaporation is proportional to fraction theta, and theta means occupied part and 1 minus theta means unoccupied part. So rate of evaporation can be written as, this proportionality sign is replaced by constant, therefore rate of evaporation can be written as rate is equal to K2 into theta. This is called as equation 2, and here K2 is the proportionality constant. At equilibrium what happens? The rate of condensation is equal to rate of evaporation. Therefore from equation 1 and 2 what we can write? K1 into P into 1 minus theta. This K1 into P into 1 minus theta is equal to K2 into theta. And from this equation what we can write? K1 into P minus by multiplying K1 into P into bracket 1 minus theta. So we got K1 into P minus K1 P into theta is equal to K2 into theta. By rearranging this equation we can got the K1 into P is equal to K2 into theta plus K1P into theta. Therefore we can write K1 into P is equal to, theta is taken common, so theta into bracket K2 plus K1 into P. Therefore for the occupied fraction, that is theta, we can write the equation K1 into P divided by K2 plus K1 into P. This is called as equation 3. Now the amount of gas adsorbed per unit mass of adsorbent, means the amount of gas adsorbed, that is X, per unit mass of adsorbent, that is M, is directly proportional to the fraction theta of the surface covered. Therefore we can write the equation X upon M, that is fraction of amount of gas adsorbed per unit mass of adsorbent is proportional to theta. Therefore we can write X upon M is equal to K into theta. This is called as equation 4. This is a proportionality sign is replaced by constant called as K, and K is the proportionality constant. By substituting the value of theta from equation 3 into 4, what we can got? X upon M is equal to K into, what is the value of theta? Theta is equal to K1 into P divided by K2 plus K1 into P. So equation is X upon M is equal to K1 into P divided by K2 plus K1 into P. By dividing the numerator and denominator by K2, this numerator and denominator, if you divide by K2, what we can got? So K into K1 into P divided by K2 divided by K1 upon K2 into P plus this K2 upon K2 gets cancelled, therefore it is a plus 1. Therefore we can write the equation for X upon M is equal to AP upon BP plus 1. And therefore, and from that equation, small a and small b, these are represented by small a is equal to K into K1 divided by K2, and small b is equal to K1 upon K2. And this equation is known as a Langmuir adsorption isotherm. So This x upon m is equal to ap upon bp plus 1. This all equation is known as the Langmuir adsorption isotherm. And this a and b are the constants of this Langmuir adsorption isotherm. So, it gives the relation between amount of gas adsorbed per gram of adsorbent and the pressure of gas at a constant temperature. And the equation gives better results over a wide range of temperature and pressure. Means in the earlier lecture we have studied that over a wide range of temperature and pressures. Means in the Freundlich adsorption isotherm it was limited to only some pressure ranges and temperature ranges. But the Langmuir adsorption isotherm gives the better results for the wide range of temperatures and pressures. And the constant A and B are the characteristics of system under the consideration and are determined from the experimental data. Means the constants in the Langmuir adsorption isotherm, that is A and B, these are the characteristics of system under the consideration and are determined from the experimental data. And the validity of isotherm is tested as follows. The equation is Langmuir adsorption isotherm equation is x upon m is equal to ap upon bp plus 1. So if we plot a graph of p upon x upon m versus p, we got a straight line having the slope is equal to b by a and the y-intercept is equal to 1 upon a. So how this graph is obtained? So by dividing the equation by this equation by p. So x upon m upon p is equal to a divided by p gets cancelled, a divided by b plus 1 upon p. So taking the reciprocal, how we can write? P upon x upon m is equal to b upon a into p plus 1 upon a. Here this a and b are the constants. By taking the reciprocal, we got the form that is p upon x upon m is equal to b by a into p plus 1 upon a. And this a and b are the constants. So this equation is of the form y is equal to mx plus c. So if we plot y, that is p upon x upon m on the y-axis and capital P, that is the pressure of the gas, on the x-axis. So we got a straight line graph having the slope of the graph is the slope is equal to b upon a and y-intercept is equal to 1 upon a. So by knowing the value of slope and intercept, we can calculate the value of a and b, which are the constants, that is the characteristics of system under the consideration. So by drawing the graph, that is p upon x upon m versus p, the validity of Langmuir adsorption isotherm is tested. So this is all about the Langmuir adsorption isotherm. So in the next lecture, we will study about the next part of the chapter, that is the factors affecting the adsorption isotherm. So thank you.